And yeah, thank you guys so much for having me. Thank you, Professor Hill, for inviting me to give one of the talks for Physics 90. I miss teaching this class. I'm sad that we can't be doing this in person. I'm glad we got an opportunity to do this today together. So Professor Hill should have sent you a subset of the slides that I'm going to be showing today. And the way I usually kind of structure a Physics 90 class is that I have a couple slides, and the slides are going to be the ones that you're going to see today that have the little Saturn image in the corner. And the idea is that, you know, I like to give not only just the bigger picture ideas, but I like to sometimes go into a little bit of the weeds. I sometimes like to give some of the details so you can see kind of how we do this as professional astronomers. But sometimes that makes it a little bit challenging to know what is the big ideas, what are the small ideas, what should I know, what should I learn, what is just kind of Aaron ranting and giving detail about. So the idea here is that if you see slides that have the little Saturn image, they will typically have a lot of text on them. Don't take notes on them because you now have copies of them. The idea then is you don't have to worry about taking a lot of notes. You can just kind of sit back, listen, ask questions if you have questions that come up on things that seem interesting. But then at the end of the day, you have the slide deck that Professor Hill sent you, and that can serve as kind of your study sheet for the content that I talked about in this lecture. So that's the idea there. All right, so let us begin. Oh, update. Betelgeuse seems to be okay. I know you guys have been tracking, the Betelgeuse has been dimming over the last couple months, but it has returned to exactly, I think as of yesterday, exactly 100% of its usual average brightness. So it seems like Betelgeuse is okay. You could ask, you know, just looking at this plot, which is showing the brightness as a function of time, you could ask, how do we know it's not gonna keep ramping up and up and up? Maybe this is just the start of a supernova. And the answer is that the slope, the rate at which it's going back to being as bright as it is, it would be much steeper. It would be getting bright really quickly if we were about to see Betelgeuse go kaboom. So Betelgeuse is probably just okay. It's just returning to its normal brightness. I think it was my TA who suggested that all we're seeing here is the Death Star finally moved out of the way, and now Betelgeuse is back to its normal brightness. So yeah, just wanted to share that real quick before we get started. All right, stars. You guys have been learning about stars, this is honestly my favorite part of the course. If you've managed to make it this far without ever seeing a star, here are some examples of stars. And the idea that we want to try to understand in the lectures you've done in the last couple of lectures and the lectures going forward is now, how do we actually know anything about these stars? How do we actually know? Because all of these stars, it's impossible for us to actually travel to these stars and actually make direct measurements. You know, and a direct measurement of temperature, for example, would mean that we go to the star and we stick a thermometer in it. Obviously, we can't do that, but we want to be able to say something about how big the star is. Is it dim because it's far away, or is it dim because it's just not very bright? Some of these stars are red, some are blue, some are white. Some are probably more massive than the others. How do we know all these properties of stars? And that's kind of the goal for these next couple lectures. Furthermore, you've now seen something like this, the Hertzsprung-Russell diagram. I would argue perhaps maybe the most famous diagram in astronomy. That's a good question. You know, you could ask, like, what's the most famous equation in astronomy? Is it E equals mc squared? Is it F equals ma? Is it Brian Hill equals professor of the year? You know, I don't know. You could debate these things. But I would say this is a pretty high contender if you wanted to argue for one of the more important plots in astronomy. I would say if it has any competition, it might be a plot you'll see later in the course where Edwin Hubble, who discovered that the universe is not only getting large, it's getting larger with time and might have originated from a hot Big Bang state. I would say maybe that plot is the only possible contender here. But you've seen here the HR diagram, a plot of the luminosity of stars, how intrinsically bright the star is, related to the temperature on the surface of the star. And what's important here, I know you've already talked about this a little bit, but what's really important about this diagram, you know, one of the big takeaways here is that it's not a complete scatter plot. stars cannot just randomly fall anywhere on this diagram. The fact that not all combinations of luminosity and temperature are possible. And the fact that the vast majority of stars fall along this diagonal, which we call the main sequence, is saying something interesting about how stars form and evolve. And the fact that there's this kind of bunching up here, which we call the giant branch, and down here, the white dwarfs. And we now know by studying the trends that first emerged on diagrams like this, that this is saying actually something about the physics underneath at play on how these stars actually operate. And it's also saying something interesting about how stars form and evolve as a function of time. This is taken from the Gaia satellite, which was launched just a couple of years ago, which does very, very precise measurements, particularly parallax measurements and observations of millions of stars in the local Milky Way vicinity. And the colors that you're seeing here is giving you an indication of how many stars there are. So these dark blues just means that vast majority of the stars fall along this main sequence compared to the giant branch in the white dwarf area. And the fact that most of them lie along the main sequence actually is already telling us something interesting about how stars evolve. It's saying, since most of the stars fall along the main sequence, that's telling you that stars spend most of their lives doing whatever they do here along the main sequence, which we now know is the part of the star's life, like what the sun is doing now, where it is just calmly fusing hydrogen into helium as a big nuclear furnace in the center of the star. You might ask, how does that make sense? How do we actually know that's the case? Bear with me, here's the analogy I like to use, though admittedly it's a little weird. So suppose I followed you around for a year. So, for 365 days, I'm following you around, and randomly, during 1 second of every day, I take a picture of you. Again, bear with. So at the end of the year, I have 365 pictures of you, where I took each picture at one random second during the day. At the end of this exercise, I would have a lot of pictures of you, say, studying or spending time in class or sleeping, because those are activities that you spend a good amount of your day doing. So there's a good chance that I will happen to catch you doing one of those activities, where, for example, I would not have very many pictures, if any at all, of you, say, I don't know, brushing your teeth. While I hope you are all brushing your teeth, you don't spend a lot of time over the course of a 24-hour day brushing your teeth, probably. So that it'd be very rare for me to happen to randomly choose the moment that you're brushing your teeth. So that is kind of the same idea of what's going on here with the HR diagram. The fact that most of the stars are showing up on the main sequence is saying that this is actually where stars are spending most of their lives. And with an HR diagram, with a diagram like this, we can start to actually ask, okay, now let's actually go and try to figure out the physics. Let's try to figure out what is going on that makes stars do what they do. Lucky for me, you've already done some of these things, so I can go quickly through this particular slide. If we want to measure properties of stars, things we might ask to start with are things like, how far away is the star? How bright is the star? Does it appear bright or dim? And then how can we use that information to say something about the luminosity of the star? Is the star itself actually giving off a lot of light, or is it not giving off a lot of light? So I can just review these very quickly. So parallax, we've all seen, I saw you have more or less a whole lecture on this before. You can demonstrate this by holding up a finger and blinking your eyes back and forth. A lot of you are around family and friends these days, so just be careful what finger you use. And whether your finger is close to your face or far away from your face, you can get a sense of how far away your finger is based on how much your finger appears to move around as you blink your eyes back and forth. Now, don't get the impression that astronomers go out at night and start blinking their eyes. Again, what we do instead is we use the baseline of the Earth. So as the Earth moves around the sun, we take pictures of the sky, at 6 months apart, and use that to get an estimate of distances. So the parallax method. Brightness is actually pretty easy to measure. Brightness, you're just asking, is the star bright or dim? And people like Professor Hill, when he actually uses telescopes to measure brightnesses of stars, he can be quantitative about this. He can actually give numbers to how much light is entering his telescope, for example. But underlying the brightness of a star, I think I'm sorry, I should have checked. You might have been calling this intensity. What I'm calling little b here, you might have called intensity I, same thing. What's going on here, though, is that an object can be bright or dim because it itself is just giving off a lot of light or not giving off a lot of light. Yes, I or B, same thing exactly. Or the object is far away. So this is the famous inverse square law for light, which I think you've already seen. And again, just to quickly review, the idea is that if you have a light bulb that's 1,000 watts, when it's right next to your face and you move it twice as far away, that light bulb will appear as if it is a 250 watt bulb. If you move it 10 times farther away, it will appear as if it is a 10 watt bulb, even though we know the light bulb itself is emitting, say, 1,000 watts. That amount of energy every second is leaving the light bulb. And this is the same sort of thing that you do every time you monitor headlights at night, for example. Whether the headlights appear bright or dim, your brain, whether you like it or not, is actually doing the inverse square law in your subconscious and figuring out whether or not a car is close or far away based on whether the headlights are bright or dim. If you're not good at that, I would not suggest driving at night. But with astronomy, in the case of the headlights, that was the case where we had a sense of what the luminosity already was, and we used the brightness in order to infer something about the distance.
I'm just going to interrupt and
sure.
To remind everybody else to interrupt, because it's more fun for the professor when everybody interrupts. And then on your looking at the car's headlights, of course, cars' headlights are spaced, and so we use spacing a lot for headlights. So, but with a motorcycle, good chance that you're estimating how far away is that motorcycle. To some degree, your mind is estimating that based on how bright is that motorcycle headlight.
Exactly. But in astronomy, usually we want to do it a slightly different way. We usually, again, we know the brightness. We can go outside, we can look at stars. Are they bright or dim? We can get a measure for the brightness or the intensity. We just talked about how we have other ways that we can estimate the distance of stars. Maybe we also have a parallax measurement. So we know the brightness of the star, and we know how far away the star is. And then you can easily algebraically solve. If I know B and I know D, I can look up pi, I know 4. I can solve for L, the luminosity of the star. I can actually figure out the luminosity of the star, how much light is coming off the star without having to go to the star, just by looking at how bright it is and knowing how far away it is. So we're learning something. The important takeaway is that we're learning something about this star, which could be hundreds of light years away. Yeah, and just to throw it in, we use the same idea, even with distant galaxies. It's the same sort of thing where we see how bright the galaxy is, and if we can calculate how far away the galaxy is, we can make an estimate on the luminosity or how much light is coming from that galaxy. So these, I think, should have been review so far. And I'll just tease something that's upcoming for you, is that sometimes we have other ways of getting the luminosity other than the method I just described. So you'll learn about a special class of stars called Cepheid variables, where there's another way you can get the luminosity of those stars. And there we can actually then, instead of using B and D and solving for L, we know L, we know B, and we can solve for D. So Cepheid variables play a very important role in what's sometimes called the cosmic distance ladder, because sometimes parallax does not quite work. And if you go to far enough distances, you have to use other techniques. You're going to learn that Cepheid variables are one of those techniques, so you can measure distances in space. All right, that was review. Hopefully now some new stuff. You could start asking yourself also, how hot is the star? What is the star made of? How big is the star? And most importantly for us, how massive is the star? And so let's look at these one at a time. So composition and surface temperature. The idea here is that we can look at the kind of light that's coming from stars. So not just how much light, whether it's bright or dim, but what kind of light is coming from a certain object. So for example, if you take the sun, you've learned about the electromagnetic spectrum. You know that the sun is emitting along the colors of the rainbow and also in infrared and X-ray and gamma ray and the whole gamut. If we were to take the sun and put the light that comes from the sun through a very fancy prism, which we call a spectrograph, you might get something that looks like this, at least for the colors of the rainbow. So this is we call this the spectrum of the sun, at least at visible wavelengths, so the colors of the rainbow. And what this is telling you is it's telling you how much light is coming from the sun at particular colors. You know, the dark areas at the top and the bottom are not just a fancy Instagram filter. They're dark because it's saying that the sun does not emit a lot of light in these rich dark reds and these rich dark blues and violets, but it does emit a lot of light in the yellows and greens. That's actually why the sun appears white, as the right combination of all of these colors, so it appears white to our eye. So it's telling you how much light is coming at different kinds of color. But you might notice one other thing as well. You might notice that on top of this nice kind of rainbow are all these little dark patches, these dark little lines scattered about. You know, is that a smudge on my screen? No, doesn't seem like it. These are actually chemical fingerprints of what is inside and what the sun is made up of. Each one of these dark lines corresponds to some sort of element, molecule, ion, something that is inside the sun is leaving a fingerprint of its existence in the light that comes from the sun. So the fact that you see all these marks, you know, when you do this professionally, when you look at things like this and you get used to staring at spectrum, we can say exactly what the sun is made up of just by looking at where all of these patterns of dark lines appear. You know, for example, you get used to doing this, you know, these two kind of very prominent lines right here in orange means that there is sodium on the sun. This dark line up here is indicative that there is a lot of hydrogen on the sun. And I think this kind of triple line in the green means that there's magnesium on the sun. So just by looking at all these patterns of lines, I think I even have an example, some of the common ones. Just by looking at these kind of dark marks across the sun and different stars, we actually get a sense of what exactly the star is made up of. So we're measuring chemical composition just by looking at the kind of light that is being emitted, which is pretty cool, I think.
Now I have an actual question.
Yes.
I found this on the web.
Siri has a question too.
So the light that you're showing there is the light from the photosphere and everything out from the photosphere, which sort of contaminates it or filters it, like the chromosphere and the corona. Are you saying that the elements and ions that are in those layers outwards are representative of what is beneath the photosphere, which we can't see at all?
Yes, great question. And you're exactly right that we are seeing the light that comes from the surface of the star, right, like the sun. So we are seeing light that is being emitted from whatever is kind of near the surface. And you're right, you know, there might be contaminants along the way, like the chromosphere or something like that. So the short answer is yes. We say that that is representative of the entire star just because of the time scales involved. There is not a lot of chemical evolution in the entire composition of the star over, you know, billions of years. The centers of the stars obviously are changing. That's, I think, your lecture on Monday. The centers of stars are changing as they fuse hydrogen to helium. But everywhere else, the composition very gradually, if at all, not at all, changes. So I would say you're right in that it is telling you what's going on the surface, but we can accurately say this is representative of kind of what's going on, what it looks like everywhere in the sun.
I think I understand. You're saying A, because the star changes slowly,
Mm-hmm.
and B, I think there's also an implication there that the star is well mixed.
Yes. Right. That essentially when it forms, that there's not a lot of settling that goes on or anything like that. That is correct. It's only really in the inner maybe 10% of the core of the star that is seeing considerable change, because that's the part where hydrogen is turning to helium, and helium might be turning to carbon and oxygen and stuff like that. Good questions. Yeah, so by looking at these patterns, we actually can tell what stars are made up of. And just as a fun aside, this actually was unfortunately going to be one of the labs we did in person. Here's the pattern that you get for helium. It kind of has this kind of 5 lines in the red, a very prominent yellow, and some blues, and maybe a violet or so, for at least in the visible colors. It turns out actually that helium was discovered on, Helios, our sun. Helium was discovered on the sun before it was discovered on Earth. The way that we did this is that, actually a lot of this came from Bunsen, of Bunsen burner fame. Unsurprisingly, he really liked to take elements and set them on fire. And he would burn different elements on the Earth, and he would see that they would glow at certain colors, and that's how we actually would determine what these patterns are for different elements. And we found this pattern on the sun by looking at the light that's coming from the sun, but we had not yet discovered an element on Earth that corresponded to this pattern of light. So we actually ended up until a decade or so later, then we discovered helium on the Earth, and realized when Bunsen kind of lit it up that actually that was what we were seeing on the sun. So helium was first discovered on the sun before it was discovered on Earth, which I think is kind of fun. Here's kind of a less pretty example, or examples of what it looks like for a variety of different stars. So what you're seeing here is how much light is being emitted at different colors. And I kind of roughly show you where the colors of the rainbow reside. So on the top, you're seeing what comes out of big stars. In the center are kind of examples of what you see for stars like the sun. And on the bottom is for stars that are smaller and cooler than the sun. And you can already see that this is showing you that different stars emit different kinds of light. Again, we're not just saying whether it is very luminous or not very luminous, but the kind of light that is coming from stars changes depending on whether you're a big star, a star like the sun, or a small star. The reason why we say big stars tend to be blue, you can see this here. You can see that it emits lots of blue light. It peaks way out here, and then it goes down and gets very dim. Versus for smaller stars, it rises and it peaks over here in the red, and then starts to go down a little bit. So smaller stars tend to appear red, and then big stars tend to appear blue, just because the kind of light that it's emitting is changing depending on whether it's a big star, a star like the sun, or a small star. And I think, remind me, Brian, that you did do in Unit 1, you did Wien's law that talked about how you can relate the temperature of a star to where this thing peaks.
Yes. So
yes.
they've seen black body spectra for
exactly
anything from like 3,500 Kelvin up to 10 or 15,000 Kelvin.
Right. That is essentially what you're seeing. You're seeing something that looks kind of like a black body curve, but on top of it are all these bumps and wiggles that correspond to the elements that are inside the stars. So the way we get temperatures, again, is we can see where these things peak. We can look at what kinds of bumps and wiggles exist, and we can tease out what the temperature of the star is and what the star is actually made up of. We know the composition of the sun incredibly well without ever having gone to the sun, scooped up a piece of its contents, and actually analyzed it. All right, cool. So this was, already in the late 19th century, astronomers were able to realize that different kinds of stars existed. There were blue stars and red stars and white stars, and they seemed to have different properties other than just their brightness. They had different colors as well. And so a bunch of people at Harvard, kind of led by Edward Pickering, they started to try to classify these stars into different kinds of stars. And again, this is not a table to be memorized. Do not memorize these numbers. You know, I don't think Brian is that tyrannical that he would ever ask you to regurgitate numbers. But this is just to give you a feel for the numbers and what we see when we look at different kinds of stars. But unfortunately, astronomers, when we first did this, it wasn't a perfect scheme. So they started to make these types of stars. So they had A stars and B stars and C stars and G stars and K stars, etc. And they made these classifications kind of arbitrarily. Like there was nothing about A stars that made them better or less than B stars and C stars. The A, B, C, D rankings didn't have any sort of meaning relative from one to the other. They kind of were just categories. So it was a little bit of a mess to understand. And it actually was the work of a bunch of really intelligent women that worked at Harvard, particularly Wilhelmina Fleming and Annie Cannon, who they were actually the ones in charge of analyzing all of these spectra. So they would get spectrum of stars, and it was, you know, it's a group of these women at Harvard that actually were in charge of doing all the analysis. And it was Annie Cannon actually that came to the realization that if you take the classifications that had already been made and rearranged them a little bit, you actually could rearrange them in a way that was a little more useful, a little bit more physical. So that's where we get this classification scheme that seems to go, you know, O, B, A, F, G, K, M, L, T, etc. Oh, for sure. Yes, this is a great example how, right. And these are classification schemes to this day that we still use, that were devised by these really, really smart women. So now the scheme, when Annie Cannon rearranged it, in O, B, A, F, G, K, M, L, T, actually, she only went down to M. L and T were added later. T actually didn't come around till the 90s. That this actually was a sequence that told you the hottest stars to the coolest stars. You know, the O and the B stars are the hottest, the bluest stars, the hottest surface temperatures. Then the A, F, G are kind of stars like the sun. K, M, and L are the cooler, redder stars. And then eventually brown dwarfs were discovered, and we added that later. And so I add this just because sometimes you'll read science articles and you'll see something like they'll refer to the sun as a G2 star, for example. You might ask, what do we mean by that? What do we mean by the sun being a G2 star? What they're just referring to is this category, this type scheme that was originated by Annie Cannon and others. Eventually, we realized that we had to be even finer in our so we created subtypes. So every letter can also have a number, like you got an A5 star or a K7 star. And the numbers just rank from hottest to coldest within the little groups. So we say that the sun is a G2 star, for example. And you might ask yourself, why did we not just rename the types? Like why OBAF, GK, MLT? Why not just rename it 1, 2, 3, 4, 5, 6, 7, 8? I don't know. I try to tell myself it's so that we have a reason to keep students on their toes. You know, because you know, you have to actually think a little bit of what these types mean, since they're all out of order. But just like you learned mnemonics to memorize the order of the planets, you know, my very energetic mother just served us nachos, you know, for example. There are mnemonics that exist for these types as well. I think classically the one is, oh, be a fine girl or guy, kiss me. Oh, be a fine girl, kiss me. And then L and T were later added, so it's lovingly, tenderly. Oh, be a fine girl, kiss me lovingly and tenderly. Which I don't know, it seems a little dated. I don't know, maybe it can be extra credit for you to come up with your own fun mnemonic as a way to memorize these. You know, maybe your midterms did not go as well as you would have liked. You know, Overlord Brian always freaking gives killer midterms. Laughing tyrannically. You know, you're gonna have fun and kind of come up with your own order of what makes the most sense. I had a student actually a couple years ago that she made the suggestion, only boring astronomers find gratification knowing mnemonics like these. Needless to say, she failed the course. I'm just joking. D-. All right, so composition, surface temperature, what stars are made up of. The takeaway here is that we can tell what they're made up of based on the kind of light that they emit. For completeness, let me just show radius. Let me come back to that. For completeness, let me just tell you how we do the radius of stars. I don't think you're going to use this equation in any large amount of way, but just to show you how we actually do this in practice. You know, we're going to leave this as an exercise for your TAs. They actually will derive this in their upper level thermodynamics classes. But there's a relationship that's called the Stefan-Boltzmann law that relates the luminosity of the star, so how bright the star is intrinsically, to the size of the star. You might recognize this as the surface area of a sphere, 4 pi r squared, multiplied by sigma, which is just a number. You can just look it up in a book, and t to the 4th power. So it's a relationship that has the luminosity, the radius of the star, and the temperature on the surface. Yeah, so that's a good point, Brian. Radius, not distance, which is important because we're talking about sizes of stars, not how far away the star is, but the size of the star. And the takeaway here, let's not actually do a calculation with this, but the takeaway here is that we've already talked about how we can measure L. We know how to measure luminosity of stars. Maybe we measure the brightness and then we do a parallax measurement, and that allowed us to get L. We did that a couple slides ago. And we just finished talking about how you get the temperatures of stars. You know, maybe you look at the spectrum, you use Wien's law, you see where the spectrum peaks. So we have ways of getting L and T. Again, I know 4, I know pi, I can look sigma up in a book. I can algebraically solve for R. I don't have to go to the star with a ruler and actually measure the size of stars. I can determine the sizes of stars just based off the light that emits, which, I don't know, I think is really cool. The fact that we can tell how big stars are just depending on the kind of light that comes out of it. So the takeaway here is that you can measure the sizes of stars based on the luminosity and the temperature. That's the takeaway. Let me just end finally with this section with masses. So how do we actually determine the mass of the star? And the best way we can do this in practice is to use binary star systems. So binary star, it's very similar to stuff you have already seen. So here's some examples of binary stars in motion. You know, binary stars, it's the same sort of idea as the Earth going around the sun or the moon going around the Earth, but instead of planets, you just have multiple stars. So just imagine the sun and you have another star that's going around the sun. That's an example of a binary star system. Binary stars, sorry, I noticed a question. Temperature for the question in the window. So binary stars are actually very, very useful in all of astronomy. I actually do a lot of research on binary stars, but I do research on binary stars when the stars are forming. In the general Milky Way, binary stars are really useful because it's one of the only ways we can actually get the direct masses of stars, where we can measure how massive a star is by watching it orbit around other stars. And we've already seen some examples of this in class. You know, Albireo, we think, is an example of a binary star system. And then here's another example of what we call a visual binary, 2 stars that are close by, clearly orbiting one another. And why I really like binary stars is because it's a great example of the physics and the ideas that you've already learned when you talked about the solar system but applied to different scales. So I know that you've done Newton's laws and Kepler's laws. And Kepler's laws in particular allowed you to relate the period of, say, the Earth going around the sun and the average distance as between the Earth and the sun, and the mass of the Earth and the sun. So Kepler's laws, I should put the equation up, I'm sorry. Kepler's law, remember, was a relationship between period, mass, and what is called the semi-major axis, or the average distance between the planet and the star. And if you remember, Isaac Newton derived Kepler's laws just using gravity. Same exact physics. Binary stars, I could write down Kepler's laws for binary stars as well. It's the same exact physics. So I could write down a Kepler's law equation for two stars orbiting one another. And it's the same idea of what you did when you did Kepler's laws for planets. We use the same exact techniques to measure the masses of stars as they orbit one another. So you can see in this case, all the stars, I don't know if you did center of mass, Brian, but the stars here, they're all kind of orbiting some kind of invisible point in the middle, which is their center of mass, which tends to be, where the most massive object is located in the case of planets. Don't worry too much about that detail. Just know that we can measure these stars going around each other. And by using the same exact version of Kepler's laws that you saw for planets, we can use a very similar version and use that to understand and actually solve for the masses of these individual stars, which is useful. It's very useful because this is really one of the few ways we have to get masses of stars. And it turns out that binary stars are actually quite prevalent in the Milky Way. If you randomly pick a star in the sky when you go out at night to do your Venus lab, there's over a 50% chance that you're looking at a star that is actually a multiple star system. Either it's actually two stars so close to one another that your eye just sees a single point of light, but actually it's two stars. Or that point of light you're seeing is actually gravitationally bound to some other point of light very nearby. Binary stars are very, very, not ubiquitous, but very, very popular ways that stars like to hang out with one another. Unfortunately, it does not seem like the sun has a binary companion. The sun seems to be a single star. We don't have a buddy. So the takeaway here is that we can, again, make indirect measurements using the same physics you saw for planets. We can measure masses of stars. So we now know everything we need to know. And so now we can start to ask really interesting questions based off this HR diagram, where the HR diagram was a function, measured surface temperature on the x-axis and luminosity on the y-axis. But now we can start to ask ourselves, particularly along the main sequence, if I know what the masses are for all of these objects, and I know how bright they are, and I know how hot they are, and I know how big they are, how the radius is, I can start to ask, what sorts of trends emerge? We already are seeing some of these trends. The main sequence, the stars lie along a very particular diagonal here. But what about as a function of mass? How is a function of mass? And you kind of can see it. It might be a little hard to see. In the red, you can kind of see 0.1, 0.3. Here's the sun, 6, 10, 30, 60. We can see how, for a given mass of a star, what does the luminosity look like? What does the temperature look like? What does the radius look like? So trends emerged. These eventually were derived, and you would derive these in kind of a graduate level course. But we have observed trends along this main sequence for stars where stars are spending most of their time. There are interesting trends that were revealed on how things like the luminosity of the star, the radius of the stars, the temperatures of the stars, how they change as a function of mass. Let's look at the radius, because I think that's the simplest one to imagine. What this equation is saying is it's saying that the radius is proportional to mass. If you've ever made a scale model, this is exactly the sort of relationship that's used. When you say a scale model is 100th, the size, that means everything was scaled down by a factor of 100. radius as a function of mass is the same sort of thing. So what this means is that if you have a star that is twice as massive as the sun, so twice as massive as the sun, then the radius is twice as big. So the radius of that star is then twice as big. If you have a star that is 10 times as massive as the sun, then the radius is 10 times as big. The radius then scales up proportionally. So more massive stars tend to be bigger, less massive stars tend to be smaller. That's all that takeaway is telling you.
I got a question about that.
Sure.
Well, so the volume of a star goes up as radius cubed.
Mm-hmm.
So you'd kind of expect, just naively, if all stars are made out of the same stuff, you might expect that the mass of a star is proportional to radius cubed. And so it's kind of a surprise that these bigger stars are less dense, I guess, huh?
That's exactly what I was going to ask you. I was going to say, like, if I were giving you an exam, I would say, what is the density of these stars? How do the densities of stars scale? And you're right, the bigger stars tend to be less dense as a result. Which, yeah, and you could ask, why is that the case? And I think it has to deal then with just the stellar structure inside of these stars, of how they may, even though they're bigger, so there's more gravity trying to crush the star on top of itself. So as a result, they end up being much more luminous, which is where we're going to get to. So as a result, they end up being kind of larger and puffier, which makes the density scale in this kind of interesting way. But what I think is the biggest takeaway here is what we saw is that the luminosity of the stars, so how much light is coming from the stars, scales as the fourth power of the mass. So what does that mean, the fourth power of the mass? Remember, that's m times m times m times m. So that means that a star that is twice as massive as the sun is not just twice as bright. It is 2 to the 4 times as bright. So 2 times 2 times 2 times 2. So 2, 4, 8, 16. A star that is twice as massive as the sun is 16 times brighter. A star that is 10 times as massive as the sun is 10 to the 4, 10,000 times brighter than the sun. Stars disproportionately get brighter and brighter and brighter as you go up in mass. And the takeaway here then is that as a result, that must imply that bigger stars live shorter lives. We really haven't talked about ages. Here's how we get ages of stars. You might ask, why is that the case? We know that stars operate by fusing hydrogen into helium. So they have a certain amount of fuel. And you might imagine that the amount of fuel they have depends on how much mass they have. More massive stars have more fuel to turn into helium. Like a truck has a bigger gas tank. But similar to the truck, the bigger stars are eating through that fuel at a much faster rate. Which is why even though trucks have bigger fuel tanks, they still get terrible mileage because they're working through that fuel at an even faster rate than, say, my small Ford Focus. So if you can imagine that if a star that is 10 times as massive as the sun might have 10 times as much fuel, but it's working through that fuel 10,000 times faster. So as a result, the big stars end up living very, very short lives. They have more fuel, but they burn through it very quickly. I think the life lesson here is that if you party hard, you'll die young. That's the takeaway from massive stars. They work through their fuel reserves very quickly. So while the sun is going to hang around for 10 billion years, it's about halfway through its life at this point. Big stars like the O and the B stars, or the big blue stars, will only hang around for about 1 million or a couple million years, which is much smaller than billions. And then the smaller stars, the small red stars, like these down here, we have actually never seen any of these stars die because they can live longer than the current age of the universe. The universe is not old enough, not enough time has passed for any of these stars down here to have died. So we don't know actually what happens to them once they run out of fuel, just because the universe hasn't been around long enough for that to happen. So big stars live short lives, which is why when we can look at things like the Orion Nebula, which has this kind of very bright trapezium of stars, super, super big, bright stars, I know that those stars can't be more than a few million years old. Because if they were any older, they would have already burned through all their fuel. They would have already died. And the fact that they're still around means they can't be more than a few million years old. And as a result, since we think the Orion Nebula all formed at kind of the same time, that means that all of these stars are roughly only a couple million years old, because we see that there are still these big stars that don't live for very long. And since they still exist, they must, this entire thing must only be a couple million years old. So let me just kind of tabulate this. Again, not to be memorized, but just to give you a sense of what some of these numbers look like. For stars like the sun, G stars, where it's about 1 times the mass of the sun, or 1.1 times the mass of the sun, is 1.3 times as bright as the sun, 1.1 times as big as the sun in radius. Where you get to really smaller stars, so only 20% of the sun, the luminosity is 8 thousandths the luminosity of the sun. The radius is only 30% that of the sun. But then you got the really big stars, the O stars, the B stars, the mass of the sun, 40 times the mass of the sun. As a result, it is 500,000 times brighter than the sun. This one star is shining like 500,000 suns, and it's about 20 times as big as the sun. So these are how these trends emerge. We saw by looking at all these different kinds of stars, we were able to get this sort of interesting data that revealed these interesting trends that then we were able to prove with physics. Now, and I just think, I just think it's the coolest thing ever, that you can learn stuff about stars without having to actually go to stars. So these interesting trends, and just for fun, again, a sun is a G2 star. Turns out the majority of the stars in the galaxy are K and M. K and M kind of rule the galaxy by number. The average star is about half a solar mass, or a star that's about half the size of the sun, is a typical star in the Milky Way. But the sun appears to be kind of roughly a garden variety star. Again, O and B stars, we don't see a lot of them because they're rare because they don't live very long. All these K and M stars, live for a very long time. So there's lots of them that have populated over the course of the 12 billion years or so the Milky Way has been around. All right, that's a good place for me to pause for any questions, because then I'm going to launch into star formation. I have about 15 minutes left, which is perfect. That's where I wanted to be. All right, and again, my style might be a little different than how Professor Hill does it. Again, like I like to go into the details, but again, since I've emailed, or Professor Hill has emailed you the slides that have the big takeaways, that's what's worth understanding. If something I said didn't quite make sense, that wasn't on one of those slides, that's okay. This is just to kind of give you a feel, an idea of kind of how we do this in practice. What is kind of interesting about all of this that's going on with how we measure and know anything about stars. All right, stellar evolution. Again, what I think is kind of the funnest part of the course. Now that we can understand and we know how to actually measure properties of stars, and we know that there are trends, and we know how to measure luminosities and masses and temperatures and all that stuff, we can start to ask ourselves, what does this look like as a function of time? How do I go from stellar birth all the way to stellar death? So your next couple lectures are going to be all about telling that narrative. It's all about a story that you're telling of how stars form, evolve, and eventually die. And the way we do this, it's hard. It's hard to do this with a single star, right? Because even the biggest stars, even though they live very short lives, the biggest stars still live for 10 million years, which is much, much longer than a human life scale. A human life scale is almost nothing compared to 10 million years. So you can't realistically expect to study, if I want to study the evolution of a star, I can't focus on one star and watch that star go all the way from birth to death. That would, that'd be more painful than watching the grass grow. Nothing would happen over the course of a human year, or human life rather, just because the time scales just are so much longer than the average time scales human lives. So instead, we look at a bunch of different kinds of stars. We look at stars that are new. We look at stars that are old. And we look at stars that are kind of intermediate, like the sun. And we get a sample of all kinds of different kinds of stars at different stages of their life. And while we're not looking at any one individual star all the way from birth to death, we can piece together a narrative that makes sense by using data from all different kinds of stars. Some of you might be in the social sciences. An analogy you might use is, if you were to go to grad school for psychology, say, and you wanted to study human behavior, your doctoral advisor would be fired immediately if they assigned you that in order for you to graduate, you have to watch one person go from birth to death. You would never finish your dissertation. You would be watching one person over the course of their entire life, and you would be in school for the rest of you'd be in school forever. Plus, what happens if it ends up that one individual is a weirdo, or I don't know, gets hit by a truck at some point halfway through? Then all your research is out the window. You have to start over. Sorry, I didn't mean for that to be so dark. But the idea is that you can't just look at one individual over the course of their entire lives. So what psychologists and sociologists and anthropologists do is they look at a bunch of different humans over the course of, at different stages in their life, and they piece together narratives and trends based on that sort of information. And we do the same sort of thing with stars. So I'm just going to talk about this first picture, how you actually get a star. Then Professor Hill is going to launch on Monday with the rest of the sequence of how you go from something like a star like the sun to more interesting things like white dwarfs, black holes, and neutron stars. So how do you form a star? How do stars come into existence? It starts, we now know, what have we learned from doing all this? We now know that stars tend to form in these large clouds of gas that exist primarily in the spiral arms of galaxies. When you do galaxies in a couple weeks, you'll learn that spiral arms are essentially just giant cosmic traffic jams. There's lots of stuff going on. Yes, it's indeed the Orion Nebula. So they're just big cosmic traffic jams, and in these spiral arms, we see giant clouds of gas like the Orion Nebula, thousands of times as massive as the sun. And in them, we see stars turning on for the first time. And again, how do we know they're turning on for the first time? Because we see things like O and B stars, the big stars that live very short lives. And again, if we see these really big stars, we know they have to have just come into existence because we know they don't live very long. So we know that what's going on inside these clouds must be, have happened recently. So we get an idea for the star formation process by looking at these clouds. And I make the joke that 9 times out of 10, the answer to everything in astronomy is just gravity. So how do you form a star? Gravity. Essentially, you get a big cloud of gas. If it's big enough, the gravity of that cloud is going to want to start to pull everything together. Gravity always wants to bring things together. And this cloud will start to fall in on itself. You can imagine like dropping a ball towards the Earth. The ball then gets pulled towards the Earth, and the Earth actually gets pulled towards the ball in that case. But the ball does most of the moving. In the case of these clouds, this entire cloud is just collapsing in on itself. And we see this happening. We see that we can actually measure and see the velocity of this gas, and we can see that it's just infalling in what we call free fall motion. Just nothing is stopping this gas from just collapsing in all towards the center. And what happens is that as this gas falls towards the center, different pockets of this larger cloud, which again is about 20 or so light years across, which is much bigger than an individual star, different pockets of this cloud start to break off, and little chunks of this cloud all start to condense together and they form little individual stars within the cloud. So different parts of this cloud. Gravity will start pulling in all that gas. That gas will start to bundle up into little balls, and those little balls, gravity will just get denser and denser and denser and denser. As a result, those balls get hotter and hotter and hotter. Eventually, if gravity can win, pockets of that cloud will turn into a bona fide shining star. That is the basic idea in a nutshell of what is going on with star formation. And again, this is the summary slide that's in it's in the email that Professor Hill sent you. Really, all that's going on is gravity is just pulling things together in these giant clouds of gas. And as these clouds collapse in on themselves, many, many stars are forming simultaneously. In the Orion Nebula, I think we have a couple thousand stars that we've observed. All of them have all roughly formed around the same time. These large other clouds of gas, all of these are individual stars that have just started turning on in the last couple million years. So stars are social beings when they form. They all form more or less together. Let's, in the last couple minutes, just kind of looking at some of the details of what's going on with this slide. So the nice thing about, well, the tricky thing with star formation, like most things in astronomy, is that the time scales are very long. It takes about 10 million years for the entire star formation process to happen from start to finish, which again makes it challenging to observe unless you do many different kinds of observations of different clouds. Another approach is that we can do simulations, which is more kind of my type of research, where I can easily simulate 10 million years on a computer. And while this is not one of my simulations, actually, it's kind of a simulation of my academic arch nemesis, Matthew Bate. But it's a very good representative simulation of what I think is going on. He's not really my arch nemesis. A little competition is always good for science. So what he has here is that he has a big cloud of gas, and we're just going to turn gravity on and let gravity do its thing. So let's press play. So gravity turns on, and you can see that gravity is already starting to pull kind of everything in together. And there's a lot of random motion as well. There's a lot of, we call this thermal motion. So it's not just everything is just collapsing into a point. There's a lot of randomness that's associated with it as well. Just how like the air in this room is kind of randomly moving around. In these giant clouds in space, there's also some thermal motion, some random motion associated with it. So what's going on? So you can see that gravity is pulling things in, and I'm going to zoom around a little bit, and a lot of it is condensing down to this region here. We're going to zoom in. And what you're going to see, let me just pause it real quick. What you're going to see is these really bright regions are going to be instances where gravity has caused the gas to collapse so much that we get what's called a protostar, a little bundle of gas that has not yet become a star, hence protostar. It's just a very bright bundle of hot gas. There you can kind of see the white dots flying around. Those are protostars. So things that will eventually become stars, as long as you give them enough time to let gravity just do its thing. You kind of can see in the upper corner, 250,000 years has passed so far. And this is roughly about 50 times the size of the solar system of what we're looking at here. Look at that, you got a beautiful little disk that flies around. In those disks are where things like the planets are gonna form. So our sun probably had a disk like this, and the planets originated in a disk like this. You can see stars are interacting with each other. Some of them are kind of getting tossed away. Got a binary star right there, that's pretty cool. Let me pause that right there. You can kind of see 2 stars in the center. So lots of things are going on. All of these stars, now that we've zoomed back out, what's happened in 250,000 years, that big bundle of gas has turned into half a dozen stars or a couple dozen stars, for example. It started like this, ended like this. Oops. You got all this interesting motion of just gravity just pulling things together, and in special little parts of the cloud, you got these little bundles, these protostars, where they're just hot balls of gas that are heating up as they gradually condense more and more and more. Eventually, if they're successful, gravity gets the temperatures in the centers of those balls of gas to about 10 million Kelvin. Nuclear reactions can then start to take place. That's hot enough for nuclear reactions to take place. I think you talked about that when you did the sun. And there you get a bona fide star. The protostar becomes a true star once nuclear reactions take place. Now, this is an example of my own work. You know, I do kind of very similar things where I study how stars form and evolve. And you can see sometimes things are a little messy. Where in this case, two stars got a little too close to one another, and well, one of them won the battle. As you can see, the others kind of just got thrown away and got tossed back out into space. Our sun might have been what happened to the sun. The sun might have got tossed out of its original cloud like this. So again, that's kind of the general takeaway of how you go from cloud to star. Really, it's just a question of gravity. You start with these big clouds of gas. You allow gravity to do its thing. This is kind of just reiterating what I just said. As gravity pulls things together, it breaks apart into these little bundles, which we call protostars. At that stage, the protostar, it's not really a free fall at that point, but the protostar is essentially a big hot ball of gas that is slowly condensing and getting hotter and hotter and hotter. And those bundles of gas eventually get hot enough. Yes, 15 million Kelvin, exactly. 15, where eventually the centers of those stars get to 15 million degrees Kelvin. And you get nuclear fusion that can take place. This is kind of also my cartoon summary slide of that entire process. It's gravity until fusion takes place. And then once fusion takes place, you get a bona fide star. That fusion actually creates enough pressure where the star can kind of just exist stably. It's no longer contracting. Gravity kind of settles and is being balanced by the nuclear forces that are going on inside the star. So you might hear this referred to as hydrostatic equilibrium. And that's all we mean by that. So an analogy is if you blow up a balloon, you know, inside the balloon is air, which has a pressure. That pressure inside the balloon is pushing against the surface of the balloon, while the rubber or the latex of the balloon is trying to cause the balloon to deflate or shrink. And it's because that they are in balance with one another. So the tension of the balloon is balanced by the pressure that the balloon just stays its same exact shape. Same idea with a star, except instead of latex, it's gravity. So you got the pressure inside the star is pushing out, gravity is pulling it in, and something like our sun, those two things are in balance with one another. So they're calmly, just perfectly balanced with one another. And then you get a star. And then actually, once you actually form a star, when you form a star, it's kind of boring. Like nothing really, the sun doesn't really change very much over the course of its entire life. What I think personally, I'm obviously very biased, I think the interesting parts of a star's life are at the very beginning when they form, where it's this chaotic collapse due to gravity. And here's some other examples of kind of star forming regions. It's the Carina Nebula, where you got a lot of chaotic motion. And you kind of can see it too if we zoom in. You can see these little pockets of gas this is where, you know, they will condense and form stars. Now, I will end with this photo, the most famous photo probably in star formation, the pillars of creation, they're called sometimes. This is in the Eagle Nebula, where these pillars are actually if we were to peer inside these pillars, we would see stars that are forming. And you kind of can see that in the image below. You know, in the top image, it's just the colors of the rainbow. And there's so much stuff here that it appears dark. We can't see. It's like a thick fog. You can't see through it. But if we look at using different kinds of radiation, you can see at the very tips of all of these pillars are very, very bright objects in the infrared. And those are actually where protostars are forming and will eventually become new stars. All right, a few minutes over, sorry for that. But hopefully that was interesting. Hopefully it gives you kind of a flavor of kind of how we know anything about stars. hopefully this sets Brian up nicely to talk about stellar evolution. He gets to do also the really cool part of how stars die, which are really exotic things like black holes.
Thank you, Aaron.
Supernova. But yeah, I'm happy to hang around if people have some more questions. Thank you, whoever just gave a shout out. Yeah. And thank you again, Brian, for letting me do this.
My pleasure. Yeah, feel free to unmute people and either just drop off because you got to go to your 9:15 class or ask any questions.